All right, so just a quick recap of the equation of change. So basically, by applying a shell balance and now having a time dependent response, I can quickly review that. Okay. So if I look at the rate of change of the total energy, so that is kinetic and internal energy within a fluid element, then that's going to be net rate of what we actually quantify with my energy flux vector, and that is energy coming into the fluid element by convection, then the rate of heat that is produced by molecular transport within that element, and also the rate of work done by molecular transport inside that element. So those three things are quantified by my energy flux vector. And then I also might have some work done by external forces, okay, as well as any energy production or maybe sink within the elements. So when I sum up those things, okay, basically we had this is my element in Cartesian coordinate system. In order to see what comes in or comes out to the element, we basically project my energy vector onto the normal coming through each of the boundary sides, and then I just sum those up. So basically, I'm going to look at the combined energy that enters and leaves through the volume boundaries in x direction, and we will essentially get that is area of this side times Ex coming in minus whatever is coming out through the same type of area. Then I'm going to look at the y sides, and I'm going to get a very similar term for y sides. Then I'm going to look at the z sides and get a similar term. So basically, I sum up all of those terms, and that's my net energy flux coming through the boundaries. Right? And then I also can have work done by external forces, and that is basically gravity force. Okay, so this is force of gravity dot the velocity vector. So basically the dot product with the velocity vector. And I didn't put sources or sinks. Sources and sinks you typically have as some sort of functional relationship that you just add to this equation if you need to. So when you sum all of those up, then basically we get divergence of Ex when I divide by volume and let delta x, delta y, delta z go to 0. So this is my standard shell balances procedure. So I will get essentially this as my equation, or shorthand notation is our favorite operator in this course is divergence, right? Everybody's like, yeah, right. Okay. So anyway, so basically the rate of change or the rate of accumulation or possibly spending some energy, total energy is divergence of this energy flux vector plus any action of the external forces. And again, if you have sources and sinks, you add them to this portion here. All right, so this is rather simple when you're using energy flux vector. We do know that energy flux vector can actually have a pretty complicated expression, and I need to know enthalpy and whatnot and do the derivatives of that. But if I actually just have stationary solid, okay, then this, so this is my energy flux vector. If I have a stationary solid, okay, then this velocity is 0. This velocity is 0. This is going to be 0 as well, okay? And basically, all I'm going to have here, this part is going to be 0. So divergence of E becomes divergence of Q is equal to 0. Okay. So if I have divergence of Q, okay, Q is minus K gradient of T. What is divergence of a gradient? Laplacian. So I get my favorite equation, Laplace equation. Again, it's omnipresent. You had it in your computational project. Okay? You had actually Laplacian of that velocity Vz. So if you do Stokes equation in a channel that might have a complicated cross-section, but that cross-section is not changing, okay? Then basically Stokes' equation for that problem comes down to Laplacian of that Vz, if your z is your long component, right? Laplacian of Vz is equal to 0, or you can basically form it both as a Poisson, if you have boundary conditions, both as a Poisson problem. Poisson problem is Laplacian equals to some function. Or you can have both are equations with names. If I'm equation with a name, that means that there's plenty of ways to solve that equation. So you can already find software to solve that equation. So this is also some problem that we found already. Where else did we have Laplacian something? There was one specific problem that showed up in the stream function approach. There's one specific case in that test problem that I gave you for is the practice exam. That practice midterm had a case where basically both stream function and a potential function were satisfying Laplace equation, and that was a little simpler than than basically doing Laplacian of the stream function is equal to 0. So basically, the Laplace equation shows up everywhere and anywhere. And today, we're going to actually solve a problem where this comes up. So we're going to actually solve a simple problem. You will notice that in our examples that we've solved so far in heat transport, there was a slit geometry, there was an averaged 1D geometry, there was annulus geometry, and there was a cylinder geometry. So what's missing? Sphere. Yay! All right. So today we're actually going to have an example, and it's going to be a relatively simple example. So we're going to do Maxwell's analysis of heat conduction in infinite domain containing a sphere. Okay? And this is going to be a steady state problem. Okay, so basically, and I'm going to have you work on it for the most part. Okay. So basically, I have the following boundary conditions. So I have a sphere in infinite domain, okay? And that sphere is of a slightly different material than the rest of the domain. So my conductivity, thermal conductivity of the sphere is K0, and the rest of the domain is K1. Now, my first boundary condition is that I have at my center of the sphere, okay, R is equal to 0. My temperature is given as T0. Okay? And other than that, all I know is that gradient in z direction of this temperature is imposed. So basically, I'm imposing boundary condition as a constant gradient in temperature. Okay? So that's something I can do in the lab, even if I don't have really, in the lab, I'm not going to have infinite domain, okay? But this is just for analytical solution of the problem. So my dt dz is a constant that I'm calling A. So it's externally imposed gradient in temperature. Especially so if I don't have a sphere at all, okay, this temperature would be just a constant gradient. Now I do have a sphere, so that dt dz near the sphere will be slightly perturbed, and we're actually going to look at how its temperature as well as its gradients perturbed by the presence of the sphere. Okay. So basically, that's what I mean, that my boundary condition is that dt dz is equal to A, or a constant, as R goes to infinity, basically very far away from the sphere. Okay. So that's how I analytically express that. Okay? And I am wondering, what is the R theta? So this is going to be, of course, spherical coordinates. And since it's a sphere, however I turn this, and this gradient is in z direction, sort of in axial direction, however I turn around, I don't expect to see anything different in cross sections, right? So I don't have really dependence on phi in my spherical coordinates. Okay? So what I'm really solving is, as we already put together, we're solving, okay? We're solving that delta where T is equal to 0 in each of the materials. Okay? So I have this K is general here. I know that it actually changes inside and outside of the boundary. And this delta square T is equal to 0 in each of the materials. Okay. So what I want you to do now is either go to the, by the way, that, can I get the textbook? That problem from, I think I solved that problem some in class or during the review, but that problem that I talked about is 4b5, steady potential flow around a stationary sphere. So either consult that problem from, that was the midterm practice, or quickly sketch out if my Laplacian of t is equal to 0, and I'm assuming that t is some function of r times a function of theta, what has to be, and given these boundary conditions, what has to be the general form of t? Okay. What is the general form of t that satisfies this? So try to look through or inform yourself by looking at 4b3 and 4b5, where we already solved that. The main problem that I have here is that this is true, and based on the form of this equation, it appears as if t is not going to depend on k0 or k1, right? Except that it will be, because I have to impose boundary conditions. So I have to have matching temperature distributions on the boundary. So this equation is valid in each material, and on boundary I have to carefully match. So if I have a general form of a solution, okay, that general form of a solution will have different coefficients within materials of different thermal conductivity. And this is classical thing for steady state problem of composite materials. Okay. You will have on the face, it looks like this simple equation has to be solved everywhere, except that you have to look at it separately in each of the material, okay, and then match the solution on the boundary in order to have solution for the entire system. Because otherwise this Laplacian of t is equal to 0 would fool me into thinking that, oh, I don't depend on thermal conductivity at all. Any luck with finding the general form? I'm just trying to cut down the work of solving this, since we've already solved it. That's the whole point of doing this course and doing different types of transport at the same time, because we can inform ourselves from something that we already solved. It doesn't really matter that it was different type of transport. Mathematical equation is equation. You need another minute?